Hello everyone, welcome back to the latest lecture session. So let's see, again, over the next couple of sessions, we are going to look at interaction or equilibrium relationships between air, water, and soil now, right? Again, I just mentioned equilibrium. Equilibrium, I guess, is a state. It tells you, how far the system can go, given what do we say, relevant conditions of temperature and pressure, let's say, right. This is again with respect to thermodynamics. Again, you are pretty much experts at it. And in general, equilibrium and kinetics go hand in hand. Kinetics, tell you how fast the system can go. It's a characteristic of the system. Equilibrium is a state, right. Is it here? Will it end up here? Will it end up here? Right, but kinetics will tell you how far it can go from one place to the other, if I may use those layman's terms. So let's see what we have out here. And we have this. So obviously phase change. For example, we talked about this earlier, oxygen in the gaseous phase, will be in equilibrium with oxygen in the aqueous phase, right. So I want to understand or use this to calculate, let's say, for example, if I use up the dissolved oxygen in the lake, again oxygen from the atmosphere is going to dissolve into the lake, but that is going to take time. But I can predict what can happen once steady state has been reached, right. So in that context, we are going to talk about phase change between gaseous, aqueous and solid phases, right. We are talking about phase change or change in phase from one to the other, and we looked at this particular example already. So in general, the system tries to achieve equilibrium, right, where it has least Gibbs energy of the system, right. So equilibrium is defined by thermodynamics, Gibbs free energy. That's something that you can calculate. So layman's terms, we say it's the final stopping place. Again, that's more or less depend upon the Gibbs energy of the system, let's say, right. Wherever it's much more stable, that's where it's going to stop. Again, typically equilibrium, it's best approach for fast reactions, as in you have acid base reactions. The kinetics are pretty fast, order of milliseconds and sometimes nanoseconds. It doesn't really matter whether you look at the kinetics or not. It does matter, let's say, if we are talking about a water droplet falling through the atmosphere and the carbon dioxide in the atmosphere interacting with or affecting the pH of the water droplet. In those cases, maybe the kinetics of acid bases come into play, but in general, in all our what do we say cases, or most of the cases, we do not look at kinetics for fast reactions. We typically look at equilibrium, let's see. Again, as I mentioned, typical cases of fast reactions, acid base reactions, most complexation and some phase transfers. Again, the emphasis is on some phase transfers, right. Again, typically we are going to deal with O2, oxygen phase change, right. And one way is diffusion from the atmosphere into the water, typically pretty slow. And the other one, which is neglected but is remarkably important, is by the photosynthesis by algae in the presence of sunlight, I guess, right. That is something to keep in mind. And for this, what do the algae need? They again need carbon dioxide, let us see, right. Again, where will the carbon dioxide come into the aqueous phase? Again, that will come from the carbon dioxide in the gaseous phase, right. Again, you have another case of phase change here, right. So let us move on and look at equilibrium or aspects related to equilibrium. So we in this course, I guess, we are going to deal with equilibrium constant. So for this particular reaction, right, where A reacts with B to form C and D, right, and what do you have? You have the equilibrium constant. What is that going to be? I guess it's going to be equal to the activity of the products. Let us say this is the reaction, activity of the products rise to the stoichiometric coefficients, right. The product of the activity of the products rise to their stoichiometric coefficients divided by the product of the activity of the reactants rise to their stoichiometric coefficients, right. Again, activity, I guess it tells you, and again layman's terms, how reactive a particular compound is in a particular system or a solution, let us say, right. It depends on both the compound and the system here, right. But in this class, we are not going to look at activity. We are going to assume that the ionic strength is, we are going to assume that the ionic strength is pretty less, right, such that activity is equal to the concentration of that particular compound, let us say, right. I think I have that here. So, what do we have? ABCD, small ABCD are the stoichiometric coefficients, that is something we discussed. Activity of the reactants and products, right, and which can be approximated by concentration of the compounds in dilute solutions, right. When we say dilute solutions, it means that the ionic strength of the solutions is low, right, and we are going to say that or approximate activity by the concentration of that particular compound here, right. So, let us move on and see what else we have out here. So, phase equilibrium, we discussed this, right. Let me go through. Well, to understand what a phase is, I guess layman's terms, again in this class we are certainly not going to ask you for definitions and such. We will try to, again we are restricted by the type of exams that we are going to have due to what is this now, the corona induced adverse effects, if I may say so. So, let us see how things pan out, pardon me, but we typically, or I typically try to avoid asking definitions and such. It is more or less your ability to think and apply the concepts that you have learned with respect to what you see out there in the natural world. And here are the building blocks that you are going to use, let us say, to be able to answer or arrive at your questions, or to arrive at the answers, pardon me. So, let us see what, but again as I mentioned, because we can't have the typical exams, let us see how things will turn out to be, right. Again, you do not need to mug up definitions and such, but to understand what a phase is, we more or less say that it is a region with uniform chemical and physical properties, gases, liquids and solids, let us say, right. Phase changes will be typically be primarily physical changes. Again, thermodynamics plays a role here. Let us move on. We are in this course going to look at gas liquid interactions pretty much. So, what are, or which law defines or helps you understand the relationship, at least with respect to dilute systems, let us say, the concentration, or what law will help you relate concentration of the compound in the gaseous phase to concentration of the compound in the aqueous phase, right. That is going to be Henry's law, at least in dilute systems. So, for example, here is a container, okay, and a closed container, keep that in mind, and I introduce a particular volatile compound here, let us say vinyl chloride. Let us say what do we say, introduce vinyl chloride here, let us say, right, or chloroform 2, or any volatile or mildly volatile compounds, let us say. And let us say I can take a syringe through this here, put a syringe through here and sample this gaseous phase and then analyze it in a GC, let us say, in a gas chromatograph, let us say, right, gas chromatograph. What am I going to get? I am going to see that there is vinyl chloride present in this particular gaseous phase. So, why is that? Even though initially there was no vinyl chloride present in the gaseous phase, as in concentration of vinyl chloride in the gaseous phase initially is equal to 0. But after some time, concentration of vinyl chloride in the gaseous phase, at let us say at time t, is not equal to 0. So, what is happening now? You are going to have phase change, I guess, right. So, obviously, the Henry's law will tell you what the relationship is between the concentration of the compound in the gaseous phase to the concentration of the compound in the aqueous phase. But keep in mind that it is at equilibrium, only when the system has reached equilibrium will Henry's law will be applicable. So, let us see what else I have here. Okay, as I mentioned, it is applicable to dilute systems. Concentrated, you have Rawls law. Again, we are not going to go into that, because mostly in environmental what do we say, engineering related aspects, we come across only dilute systems, or as we say, mole fraction in the liquid phase is small. And what does it state? I guess again, as I mentioned, it gives you the relationship between concentration in the gaseous phase to the concentration in the aqueous phase, right. Henry's constant will give you the concentration in the gaseous phase to the concentration in the aqueous phase, right. So, that is what we have out here. States that the amount of gas that dissolves into a liquid is proportional to the partial pressure that the gas exerts on the surface of the liquid. So, here we say that it is the partial pressure, but keep in mind that depending on the units, right, say you can have H you have H dash, the partial pressure by concentration in the aqueous phase. So, Henry's constant, right, H, let us say, can have different units. So, keep that in mind. Depending on the type of units, you are going to have to look at the relevant numerator and denominator, let us see. So, again let us move on. So, where does that come from? Let us say you have this particular reaction, let us say reversible reaction, and one example is with respect to oxygen. So, at equilibrium, what is it going to be? You are going to have what is it now, the equilibrium constant, activity of the compound, what do we say now, compound, the product, I guess, right, the product being the gaseous phase by activity of the reactants, which is the aqueous phase, right. So, that is where we get this from, equilibrium constant. So, in this context, we have that equilibrium constant, it is referred to as the Henry's law constant, and as I said, the activity coefficients are normally considered as equal to 1. For example, activity is equal to an activity coefficient times concentration. So, what we are saying is that in dilute systems, which is the case that we are most usually going to or frequently going to encounter in this course, we are going to saying that activity coefficient is equal to 1. Thus, activity is almost equal to concentration, right. So, that is something that we have. So, that is why we say that again K as Henry's constant, and activity we are replacing that by concentration, let us say, right. And as I mentioned earlier, note that assumption about activity coefficients, right, depending upon activity coefficients gives H units, and many different types of H are used. For example, we can have, as I mentioned, H is equal to partial pressure by concentration in the aqueous phase, right. So, units obviously are going to be, let us say, can be atmospheres mole per liter, that is what we have out here, right. So, what else? We can have partial pressure per mole fraction, right. Again, these are the units of the concentration in the aqueous phase, mole fraction. Again, it depends on the units of H, right. That is what you have to pay attention to. It can be mole per liter, again dimensionless, typically dimensionless Henry's constant, let us say we have this. And again, obviously, what does the higher H mean? Higher H means that the numerator is typically higher, right. And what does that mean? It means that the compound would prefer to stay in the gaseous phase, right. As we just said, H is concentration of the compound in the gaseous phase to the concentration of the compound in the aqueous phase. So, higher H means typically the compound concentration of the compound in the gaseous phase is higher compared to the concentration of the compound in the aqueous phase. So, again, what does that mean? The compound prefers to stay in the gaseous phase. That means that the compound is volatile, right, relatively more volatile compound. Effect of temperature typically increases H, that is something that you can understand even from thermodynamics if you look at that, but we are not going to dig into that. Sometimes let us say again instead of H, people use KH and write the reaction in the reverse direction, right. You can see that out here. Instead of aqueous going to gaseous, you have gaseous going to aqueous, then the term that you are going to use or the variable that you are going to use is KH, not H, I guess, right. So, that is something to keep in mind, and obviously even if you cannot remember this as in which what do we say, H or KH refers to which particular proportion of aqueous and gaseous phase concentrations, you can always look at the units out here, right, and that will help you understand this. For example, I guess here they are saying Henry's constant, but again KH, but as you can see, what are the units out here? You have 10 power minus 3 molar atmospheres, right. So, molar meaning mole per liter by atmospheres. So, from that you can understand that it is KH is equal to concentration in the gaseous by concentration or partial pressure, right. So, that is what you have out here, right. Just pay attention to the units and you will be fine. Again, what do we see with respect to KH? We see that with the increase in, as we mentioned earlier, with the increase in temperature, typically we see an increase in H, right, meaning the compound would want to stay in the gaseous phase, right. And obviously the reverse, what does that mean now? When temperature increases, KH is going to decrease, I guess. Well, that is a no brainer out there. So, that is what you see out here, right, as in that KH decreases with increasing temperature. So, what does that mean? When I increase the temperature, the concentration in the gaseous phase decreases. Is it gaseous phase? I guess that is a type out there, that is the concentration in the aqueous phase, concentration in the water, let us see, decreases, right. So, what is the practical importance or relevance of this aspect? As in typically in summers, you are going to have high temperatures, right, and you are going to have remarkably or not remarkably considerably higher rate of biological degradation of any organics that you put into the river. But again, as I mentioned, I am not sure if I mentioned this, but microbes play the role of catalysts now. So, they still need an electron acceptor and an electron donor, right. Electron donor is obviously the reduced form of the organic compound that we or the industries release into the lake or the river now. But what is the electron acceptor now? It is typically oxygen, right, and oxygen again, as you see in summer months where you have increase in temperature, the what do we say, saturation levels of oxygen are going to be relatively low. So, the kinetics of the this aerobic degradation are higher, but the maximum oxygen that the river or the river water can hold is less. So, that is a double whammy. So, you are going to have typically anaerobic conditions prevailing if you have organic content during summers, I guess, or relatively quickly you are going to reach anaerobic conditions. Again, what is the implication? In the summer, the rivers and lakes will have less dissolved oxygen compared to dissolved oxygen in the winter. Again, that is a no brainer, that is something that we just looked at, but keep that in mind, I guess, right. So, different relevant compounds, and you have the KH out here, it is general information, we are not going to look at that. Typically, we do not use this variable, we are typically concerned with KH or H, right, Henry's constants only. So, again, which one is more volatile and which one is less volatile, that is something that you can look at, right. And we will look at applications of ideal gas law and obviously the law of partial pressures. I guess you are the experts here. PV is equal to nRT, right, PV equal to nRT. So, molar concentration, which is number of moles per unit volume, is equal to P by RT, I guess, right. PV is equal to nRT, right. So, what do we have? P by RT is equal to the molar concentration out here. Again, it seems what do we have here? Partial pressure of each gas in a gas mixture, such as in the atmosphere, let us say, is the portion of the total pressure that a particular gas would exert, let us say, right. It is that particular portion. For example, here I guess you have a mixture of gases, and what do we have? We have helium and hydrogen, let us say, right. And as you can see, here you have the partial pressure out here and the molar concentration, if I may say so, and similarly partial pressure out here and molar concentration, right. So, what do we have? It is proportional to the partial pressure of each gas is a portion of the total pressure that a particular gas would exert. That is a no brainer, but here is what I wanted to look at. Where is that? Okay, the law of partial pressure states that the total pressure of a mixture of several gases is the sum of partial pressures of the individual gases, right. So, that is what you see, total pressure is the sum of what is this now? The individual partial pressures, I guess, right. So, P total, partial pressure of hydrogen and partial pressure of helium, so on and so forth, and we have we looked at this relationship out here. So, again total number of moles, that is what you have out here. Again, why is it important, or why are we going to look at, or why are we looking at this particular what do we say, Dalton's law? Because we are going to have increasing and decreasing levels of carbon dioxide, let us say, either locally over a city or in the global or in the world itself, right. And that is going to affect the carbon dioxide concentration that is going to be in equilibrium in the aqueous phase, and then what is going to happen? You are going to have a decrease in pH and then effects on aquatic life. So, I guess in that context we are looking at this, so that is something to keep in mind out here, right. So, let us move on, and here I guess we have a example. Find out the DO in aerated water at 25 degrees centigrade in a treatment plant, let us see. Okay, find out the DO, and what is the information that we have? We have KH to be equal to this particular value at 25 degrees centigrade. So, looking at the units, I guess what do we have kH, it is molar units up here. So, concentration molar units, let us say concentration in the aqueous phase by the partial pressure, right. This is with respect to oxygen now obviously, and this is with respect to dissolved oxygen. It is equal to 1.26 into 10 power minus 3, right, and molar units per atmospheres. So, let us see how we are going to go about it, right. Again molecular weight, I guess, right. So, partial pressure of oxygen in the atmosphere, it is 0.21 atmospheres approximately, and as we just looked at, this relationship is nothing but what we have out here, right. kH is equal to concentration of oxygen in the gas in the aqueous phase by the partial pressure of oxygen, right. And what do we have? We have partial pressure of oxygen to be 0.21 atmospheres, we have this value, and so you can figure out what the approximate dissolved oxygen concentration is going to be in the treatment plant, let us say. For example, in different cases you have to have water, not have to have water, you have to have water at a particular DO or minimum DO level. So, what do you do, or what do people do? They put in diffusers, let us say, where you bubble air through that, right, you bubble air through it, and over time you are going to have relevant what do we say DO level. So, here we are trying to say that or ask, let us say, what is this DO level going to be, assuming that the equilibrium has been reached. Keep in mind that the Henry's law is applicable only when the equilibrium has been reached. So, we say we can calculate that by approximating the partial pressure of oxygen in the atmosphere, right, because here you are pumping in air, you typically pump in air, right, and you know that the partial pressure is 0.21 atmospheres, and we have the Henry's constant at that particular temperature of 25 degrees centigrade. So, let us see what the value turns out to be. It is kH into 0.21 atmospheres, and the value comes out to be I guess pretty low, 0.26 millimolar, and that is equal to 8.467 milligram per liter, right. So, that is something to keep in mind. I think we looked at this example, or not example, pardon me, we looked at the case of dissolved oxygen when we were looking at, I think, acetic acid being dumped into a river or being discharged from a treatment plant at 50 milligram per liter concentration, right, 50 milligram per liter concentration, and I think the flow rate was what, 500 meter cube per day, and I think you solved it to you figured out how much oxygen was required to what do we say oxidize this particular acetic acid, and I think you got what, 2.6 kgs per day or something like that, right. So, as you see or in that context we try to understand or we try to look at why it was a considerable value, as in even though 50 milligram per liter of acetic acid seems to be pretty low, we saw that what do we say considerable amount of oxygen is required. And why do we say considerable? Because in water what is the maximum DO that can typically be held at 25 degrees centigrade? It is only 8.4 milligram per liter, right. So, 2.6 kgs per day, again you can have the flow rate and such and dilution, but again this is a remarkably high value. So, in that context we already looked at it as in the typical dissolved oxygen values, I guess, right. So, let us move on out here, and then other aspects are with respect to air water interactions, and in this context we are looking at rainwater droplet that is falling through the air, let us say. And what do we have? We have carbon dioxide in the atmosphere that is now going to try to dissolve into the water droplet, and O2, SO2, organic acids, aerosols, dust, NH3, right. So, as the droplet passes through, you have different compounds out there in the gaseous phases, and they are going to try to reach or dissolve into the aqueous phase, let us say, to try to achieve equilibrium, let us say, right. So, depending on the time and the kind of reactions, if it is acid base, and again depending on the kind of acid base reactions, typically the kinetics are pretty fast, and so the equilibrium can be or will be probably reached, let us see. So, so we are assuming that the species typically establish, keep in mind that this is an assumption, species establish a quick equilibrium, meaning the kinetics are fast, I guess, right. Again, why is that relevant? Because given the carbon dioxide concentration or even NO2 concentration or NO concentration in the atmosphere, you can calculate what the pH of this rain droplet is going to be, and see that if it can lead to cases of acid rain, right. So, in that context, you need to be able to understand, obviously, the air water interactions, right. So, that is something I guess we will be looking at. So, as I mentioned, one of the applications is with respect to dissolution of gases, right, as rainwater falls to the ground, and the other one is with respect to aeration in an activated sludge system. Depending on how or where you are, next semester, as in at home, or are you going to come here to the campus, and if we are going to be allowed to interact with you face to face, right, we are going to go and visit a sewage treatment plant out here, right. Obviously, we do not want you to bore you to death looking at these videos. We want you to gain some practical knowledge. So, when you go there, you will see that this is how your waste will look, and you will add microbes, right. You will add microbes, Why? Because I guess they play or release enzymes which act as catalysts. Okay. Again, this is just for general knowledge. So, these but again you need to have an electron acceptor and donor. So, you have our sewage, which let us say is a relatively reduced form of carbon, and that needs to be mineralized to carbon dioxide, let us say, and water. But for this you need an electron acceptor, because this is the electron donor. So, you need an electron acceptor. So, what is the electron acceptor? As we mentioned earlier, it is going to be oxygen. So, you are going to pump oxygen through your waste to provide electron acceptor for your microbes, let us say, right. So, that is something that we just solved out here, right. And what was the value that we had or end up with? We end up with 8.4 milligram per liter, but rarely will you achieve that. Why is that? Because well, let me ask that in the exam, I guess, right. Anyway, so we are going to have stripping of ammonia, let us say, right. For example, NH4 plus does not really want to stay in the gaseous phase, NH3 yes can or can exist as gas, let us say. So, depending on the pH and the speciation, you can remove nitrogen from water by bubbling air through it and stripping ammonia in that way, I guess, right. You will change the pH and then what do we say, bubble air through it by air stripping, I guess, right, or stripping ammonia. And then carbonate system, this is something we discussed. Carbon dioxide in the gaseous phase is going to be in equilibrium with the one in water, and that is going to, what do we say, lead to dissolution of CaCO3, calcium carbonate deposits, right, and that is going to again change the equilibrium a bit, and so on and so forth. We are going to look at these calculations later, right. So, again different air water interactions, let us say, right, gaseous phase and aqueous phase interactions. So, one other aspect is that after change in phase from gaseous to aqueous, obviously if it is an acid or a base, they will what do we say, affect the pH, right. So, again in environmental engineering or in any environmental aspects, not engineering itself, pH is a remarkably important aspect or variable. So, we call that the master variable. Did I skip something? Okay. So, pH of most mineral bearing waters is 6 to 9, okay, but typically let us say we are fine with 6.5 to 8, right, at 6 to 9 is too wide a range. And the pH and composition of natural waters is regulated obviously by the reactions of acids and bases. Again, everything is going to be in equilibrium typically in the natural systems, right. And chemical reactions obviously again mostly with minerals. So, in the context of this dissolution of carbon dioxide, what is going to happen? Let us say you bubble carbon dioxide through water, and that water comes in contact with your calcium carbonate solid, let us say, right. What is going to happen? That is going to lead to dissolution, I guess, right. Typically, I guess you have CaCO3 solid, Ca2 plus CO3 2 minus, let us see, right. Again, we will look at this again in detail. This is the solubility product KSP into CO3 2 minus, right. Again by the activity of solid is going to be 1. Again that is going to lead to dissolution of your particular what is this now CaCO3, right, and you are going to end up with this particular kind of reaction, but again we will look at this in greater or better detail later on. Again acids from volcanic activity, HCl and sulfur dioxide, again biological reactions as in photosynthesis and respiration, again, right, all are dependent upon pH here. Again you see the relevance of pH here in the sense that CO3 2 minus and calcium can also form aqueous complexes. CO3 2 minus is dependent upon the pH of the system, right. If there is more CO3 2 minus, the system would go in this way. If the pH is less and CO3 2 minus is less, the system is going to go in this way, right. So that is something we will work out later. So equilibrium is rapidly established in acid base reactions, as I mentioned earlier, because the kinetics are pretty fast. As I mentioned, H plus is a master variable, right, because it leads to obviously acid or plays a key role in acid base reactions, also in aqueous complexes, also in precipitation and dissolution, and also in redox reactions, but not but yes, H plus plays a considerable role in all these environmentally relevant reactions, I guess, right. Again what else do we have? Strength of acids and bases, again that is something going to be dependent upon what do we say, acid dissociation constant, we are going to look at that. Strong acids obviously have a substantial tendency to donate a proton, right. Let us look at what this is about. So, for this particular reaction, right, where you have H2CO3 dissociating into H plus and HCO3 minus, right, it is obviously a reversible reaction. You are going to have what do we say, the equilibrium constant, right, and that, as we mentioned earlier, was going to be equal to the product of the activities of the products. So, that is why activity of H plus into activity of HCO3 minus divided by the activity of the reactants, which is H2CO3. But as we mentioned, we are going to approximate activities by concentrations, right, and that is what you have out here. And from this again the minus log K1 is equal to pK1, the first acid dissociation constant for H2CO3, right. You see the acid dissociating into H plus and HCO3 minus. So, we call this the first acid dissociation constant. Why first? Because as you can see it, H2CO3 has 2 protons, and here we are only releasing or looking at one what do we say, release of 1 proton. The HCO3 minus can further dissociate into H plus and H or CO3 2 minus. So, for this you are going to have K2, the equilibrium constant, and minus log K2 will be equal to pK2, let us say the second acid dissociation constant, pKa1 and pKa2, right. So, obviously here pKa1 is 6.3 and I believe pKa2 is equal to 10.3 or is approximately equal to 10.3. Well, I guess why are we looking at this carbonate system in detail now? Again, because carbon dioxide present in the gaseous phase, again the levels of carbon dioxide are going to affect the levels of the carbonic acid in the water, and that is going to again lead to dissolution of different metals or minerals, right. Again that will change the equilibrium, let us say, and that can affect the aquatic life and thus again affect our life, I guess, right. So, I guess with that I seem to be out of time. So, I will not what do we say, keep you here further, and thank you for your patience.